Welcome to the design of shear connection. One type of shear connection is double web angle connection. I'll explain the design of double web angle connection through a numerical example. So in this example, the dimension of beams and columns are defined. So the size of the column is ISHP 200. This is the column, and this is a beam where it is ISMB 250, which is to be connected by a double web angle. That is cleat to be an angle to be placed on either side of the web. That is why it is said to be double web angle connection. It predominantly transfer shear, therefore it is said to be shear connection. The design principle says that here there are two groups of bolts used to connect the beam to the column. One group of bolts connecting the beam to the cleat angle. So in this group of bolt is subjected to in-plane rotation. So I hope in your previous course you have studied about a bracket subjected to in-plane rotation and outer plane rotation. The same principle are going to be used in the design of double web angle connection. So in this group is subjected to in-plane rotation. But there are another group of bolts which connecting, that is this group of bolt I have represented in the other view, that is this bolts are connecting the cleat angle to the column flange. These bolts are subjected to out of plane rotation. So what we are going to do is, in this particular group, we are going to see how much shear is going to transfer in this particular group of bolts, and we are going to calculate what is the resultant force on the critical bolt. If the resultant force on the critical bolt is less than the bolt strength of this group, then this connection is safe. The same way, we are also going to see under out of plane rotation, the critical force on any bolt, if it is less than the bolt capacity, then the connection is safe. This is the fundamental principle you're going to use it in this connection. So we'll proceed to the discussion on the connection. So first we'll take all the design data. First we'll take the section details, and here before going for the connection, we have to decide what will be the size of the bolt. We can go for it, as well as the size of the cleat we have to decide during the process of the design. So first I assume the bolt size of M20 of grade 4.6 grade and the structural steel of 410 structural steel. So coming to the design property, so this is the stress. There is a yield stress and ultimate stress of the cleats and rolled sections. This is the ultimate stress and the yield stress of the bolts. Because of it is 4.6, I take the ultimate stress appropriately, and the yield stress is nothing but 60% of the ultimate stress to get the yield stress of the bolt. And I'll take the section property of the columns and beams. Then I'll take the suitable partial safety factor. This is the partial safety factor material, and this is for bolt. And here in the problem itself, I have given with the reaction. So what it is given as here, the length of the beam is said to be 5 meter and subject to an equivalent UDL of 110 kilonewton. That means the total load coming on the beam to the connection is 120. It is, though it is UDL, but it is an equivalent UDL. It is given as a total force. So at this junction, the beam going to transfer a reaction of 110 kilonewton. So that I have mentioned here. So the reaction expected at this interface, so the beam has to move because of this vertical reaction with respect to the column. The connection going to resist the reaction 110 kilonewton. First I'll take the connection between cleat angle, or this is said to be web angle, whatever the name you can use it. So here I represent this angle as a cleat angles. One of the cleat angle leg is connected to the web of the beam. So in this connection, the bolts group are subjected to in-plane rotation. So each and every bolt group is undergo a shear, in-plane shear, as well as a rotation, in-plane rotation. So we'll see to it how to calculate that critical force. Before going for the calculation of critical bolt resultant force, we'll calculate what is the bolt strength in in that bolt group. So here I show this is the bolt group I have taken to calculate the strength of the bolt. See here, this is the bolt group. So this is the bolt group. Here one cleat, back of the web of the beam another cleat. This is the web. So for to represent that, this is the web of the beam. Here it is a cleat. Here it is a cleat. So this bolt strength, I'm going under this arrangement, I'm going to calculate the strength of 20 mm bolt. So the diameter of the bolt is 20 mm. I have assumed standard clearance. Therefore, I calculate the necessary parameters, and it was observed that under shear the bolt is sheared about two planes, therefore the bolts are under double shear. So you have to calculate double shear capacity of the bolt. So I consider one is at the threaded region, one is at the solid region. So I have calculated net area and one plane against solid area, that is shank area. So I calculate the shear capacity and the double shear. I'll get the higher capacity because it has two shearing plane to resist the shear. Coming to the bearing capacity of the bolt, I calculate the that is a end distance minimum maximum according to section 10, and I consider the end distance will be 35, and from this I'm going to see what will be the size of the bolt. I can go for it. So see here, I should go for a size such a way that I should take a angle size based upon the back angle distance. Back angle distance is nothing but from this end to the center of the bolt hole is back angle distance, and this is the edge distance. So from this here, I consider my back angle distance is approximately 28 or 30. You can have, or take it from IS. SP6 part 1 in page number 168. You take a suitable back angle distance. Here I took the back angle distance is 28 mm. Therefore, it is only an approximate because I have not yet decided the size of the angle, cleat angle. Therefore, I take the appropriate back angle distance 28. So this is my edge distance. If I am taking the two values, back angle distance and edge distance, I could get what will be the length minimum to be go for it. So I'll get a length of the angle will be 65. Therefore, I'm going for better. I'll take the equal angle sections. So here ISA 65 cross 65 cross 8 mm. Here the thickness of angle is taken to be 8 mm. And I calculate the pitch with respect to the minimum maximum. I took a suitable pitch distance. If I know edge distance, pitch distance, I could calculate KB, from which I calculate what is the bearing capacity. So among the two, the bearing capacity is found to be lower. Therefore, the bolt strength, here the I represents in-plane rotation. The bolt strength in in-plane rotation is governed by the bearing strength of the bolt. That is, this should be taken here. So from which if this is the one capacity, this group of bolt, I have not yet decided the number of bolt required in this particular group. I know what is the shear coming here, that is the shear force coming in this bolt group, that is your 110 kilonewton. I know what is the capacity of one bolt, from which I calculate what is the number of bolt required. So here I found that there are 3 numbers of bolts are required. With this one, I'm going for arranging that bolt with the web of the beam. I should calculate what will be the height of the angle to be required, because here the H1 is nothing but the clear height or clear plane surface of your web plate. This you can get it from SP6 part 1. So you should see to it your actual length of the angle should be well within your the plane height of your web of the beam. So here it is coming like this 190 mm. Therefore, you are going for a height of the angle 190 with the 3 number of bolts. Right. Okay. You are going for 3 number of bolts subjected to a shear. So I'm going to see now I got the capacity of the bolt in this bolt group, the capacity of the bolt is nothing but 51.728 kilonewton. I'm going to calculate the resultant force under this bolt group, that is the bolt group in plane rotation condition, that is the connection between the angle leg to the web of the beam. So here there are 3 bolts available. I know that because of here this is the bolt line, and the force is transferred exactly at the contact surface of beams and the angle. See here, this is the surface the load has to be transferred. Therefore, from this to this distance is nothing but back angle distance. So this shear force exactly transfer between this column face of the column face. Therefore, here the applied reaction is eccentric to this bolt group. Therefore, you have a shear and a rotation, in plane rotation. So, regarding the shear, you will get the shear force, total shear force divided by number of bolts. You will get what is the vertical shear taken by one bolt. And you know that eccentricity, that is, this eccentricity is nothing but beam web. So this is the eccentricity in the beam web. So that is nothing but back angle distance, from which I calculate what is the in plane moment, which is equal to shear force into the eccentricity. So I'll get the moment. So if I know the moment, the horizontal force or the resultant force in this bolts could be estimated by this expression. So here I took the extreme bolt, that is, this is my extreme bolts. So I named the bolt as R1, R2 and R3. So R1 and R3 are farthest from the CG of the bolt. Therefore, I'll take the maximum force and I'll take the critical bolt. The critical bolt always falls closer to the application of the force. Therefore, I'll take that force here. So here, I already said that this force is exactly normal to the radial line. So this is your radial line. So exactly here it is horizontal. So this is acting exactly vertical and this is exactly acting horizontal. So I'm just calculating the resultant force. So resultant force will be this much. That means the under in plane rotation, the farthest bolt, this bolt is subject to a maximum shear of, sorry, a maximum force of this much. So here this magnitude is less than your bolt capacity. Therefore, this bolt group is safe to take this reaction. So, by which we will conclude the connection of the cleat to the web is safe. Now we move on to the connection between the bolts connecting the angle leg to the column flange, where this is the bolt group I'm talking of. So these bolt groups are subjected to out of plane rotation, and here you can observe that since you are going for 2 cleat angles on either side of the web, so here you have 2 groups of bolts in the on either side of the beam of the web of the beam. Therefore, you are going to see take any one side of the bolt group and we are going to check the capacity. So, I am going for the connection between cleat angle leg to the column flange. As I told that these bolts are subjected to out of plane rotation. Because of out of plane rotation, some of the bolts are under tension, some of them are in compression. So, this theory we already learned in the previous course. So I'm going for before going for the checking the resultant force, I'll check the bolt capacity. So here again I'm going for the calculation of bolt capacity under this connection. So here what happens is here, in this case the shearing plane will be single. So here we are going to see what will be the capacity of bolt under single shear condition. So therefore here I took the shear failure plane will be on the shank region. Therefore, the capacity of the bolt to be calculated by this expression, and bolt in single shear will be like this. Then I am going for since the under this case the bolts may subjected to shear or bearing. Therefore, I am calculating the bearing also. So follow the same case and you calculate what is the bearing capacity. Out of this two, again this is going to be the say lower one. Therefore, this is your bolt capacity in out of plane case. Here, as I told that since the ball group is subjected to out of plane rotation, the balls are subjected to tension. Therefore, according to the clause given in section 7, I calculate the tension capacity of the bolt. So, after knowing the tension capacity, I'll go for this resultant force acting on the ball group which are under out of plane rotation. So here, since there are two groups of balls are under out of plane rotation, I'll take one group. Therefore, shear force on one group is said to be the total shear force divided by 2. Therefore, this will be the shear expected at this ball group. Again, it is going for to take that shear, how much bolt to be required for this group. Therefore, you divide the shear by the shear capacity of the bolt or bolt value under the out of plane rotation. Therefore, we found that there are two bolts are required on each side of the uh, web of the beam. Therefore, we'll go for checking the capacity of the bolt under this condition. See here, as I have told that here, this is the bolt group I am presently discussing. Again, this here at this juncture, the shear force is expected to transfer. So CG of the, though the loads is shared along this plane, the CG of the load is expected here. Therefore, again, this group is also subjected to an eccentric load. So this will be the eccentricity. To calculate eccentricity for this bolt group is nothing but this distance divided by 2. What is this distance? It is nothing but the gauge distance, which is nothing but the column flange gauge distance. It is nothing but this, the difference between the two group of bolt which is under outer plane rotation. So from this SP6, I have taken this figure and to explain what is G. So from this SP6, for this column section, I refer this gauge distance. It is given as 140 and 100. For this problem, to reduce the eccentricity, I consider 100 mm. Therefore, I know what is the shear. Why this is 55? Since I equally divide the given shear into two groups. Therefore, shear on one group and the corresponding moment is nothing but this shear force into the gauge, half of the gauge distance to get the moment. So here, under this out of plane moment, these bolt groups are subjected to in plane shear and a tension. So see, we will calculate the in plane shear is nothing but this divided by number of bolt. Here n of 2 is n of z out, n of o is nothing but out of plane rotation number of bolts under this case. So I'm interested in calculating the tension in the bolt. So this is the expected stress state in the bolt under out of plane rotation. Through the literature, we came to know that the CG of this the moment in the out of plane moment falls at a distance of 1/6 to 1/7 of the depth from the extreme bolt CG to the bottom of the cleat angle. Here, from this CG of the top of the bolt to the bottom of the cleat angle is said to be 125. So 1/6 to 1/7 of this 125 to be taken as approximately the depth of the neutral axis. Here I have considered 1/6 of this distance as the neutral axis. So here I have calculated this distance is nothing but 20.83. If this is what 20.83, the rest of the distance is said to be tension. So from which we know that above this neutral axis, the bolts are under tension. So here all the bolts are under tension and some of the cleat is under compression. So since the cleats are under compression, so the resultant compression will act at a distance of 1/3 from the base of the stress block. So this 1/3 distance, so I know what is this distance, which is nothing but 20.83. Out of 20.83, this distance is 1/3 of the distance. That will be said to be 6.94. So by knowing this and you apply the equilibrium equation, so this is the distance I calculated. We know that this equation. So I am interested in getting the maximum or critical bolt tension. Here my critical bolt is first bolt. I want to know this T1. So where T1 is nothing but the moment cause out of plane rotation into the small L1 is nothing but from the CG to that distance, and capital L is nothing but the CG of the compression to CG of the respective tension of the bolt. So I calculate sum of this values, and I calculate this denominator as a numerator, then from which I got the expression. To know about more about this expression, please refer the last semester course. So once you know the tension and the shear expected on this bolt, this is the shear, in plane shear expected on the bolt. The code says that according to clause 10.3.6, when the bolt is subjected to combined shear and tension, then this interaction equation has to be satisfied. Therefore, I'll take what is the in plane shear is coming on the board, and this is nothing but here as per the code it is said nothing but shear capacity of the bolt, and this is the maximum tension in the bolt, and this is the tensile capacity of the bolt. When I'm making this ratio, this is coming within 1. Therefore, these bolts are safe in the combined effect of shear and tension. Therefore, this bolt group is also safe to take your shear. Now we have designed the adequacy of this bolt as well as this bolt to taken care of the applied shear. Finally, you check that whether the angle is safe under tension. We have checked the both groups under in plane rotation as well as out of plane rotation, whether this angle at this junction able to take the shear. Now, there are two angles present in the connection. Therefore, I'll take what is the shear in one angle. Therefore, I'll take that is half of the shear. I'm going to calculate what is the shear capacity of my one angle. So, my shear area is nothing but I'm going to calculate what is the design shear. So, for which the design shear area is nothing but along this line the beam has to move. Therefore, this is my shearing plane. So where it is nothing but length of the angle into thickness of the angle at which it undergo shearing failure. Therefore, length of the cleat, that is 190 mm, into the thickness of the cleat, it is nothing but 8 mm. This is your area of cross section, and you substitute in this expression, you will get what is the capacity of the cleat angle. So this capacity is larger than your shear coming on the thing. Therefore, your angle is also safe against to take the shear. Therefore, the connection is safe to take the given shear. This is all about the design of double web angle connection. Thank you.